started. So today is our last real lecture. Thank you for staying. And next Monday I will come. Because technically we have one more slot, but I won't have any prepared slides or anything. I'm just here to answer questions. If you want to, so you can come and you can, if you want me to go over any part of the previous lectures, we can do that. If you have any questions about some of the practice questions, we can also do that. It's really up to you. So if anything is confusing when you're doing the review, you can let me know, and we can talk about it on Monday. And this last lecture is about parallel graph optimization. So actually, this is a bit different. This is more probably on the practical side than what we have been doing so far. But so far we've been doing mostly theory and algorithms. And this is still algorithms, but it's more about what I would say is algorithm engineering, or practically how do you make these things run fast in parallel, and the focus is on shared memory graph optimization. Yeah. There will not be a long form question on this in the exam, probably. It's a bit hard to design one, but I thought it's interesting, so I'd like to talk about it. Okay. So we are studying graph optimization, running algorithms on graphs, practically. And this is kind of a theme, but so far we know that matrices are sparse, usually, in practice. And because there's this duality between graphs and matrices, graphs are also often sparse in practice. So yeah, they have these properties. They're large, but they're not too big in the sense that the largest publicly available graphs, they're not on the size of petabytes or something. This is some examples. So these are publicly available graphs that you can just download from the internet. So Twitter, they took the snapshot of it, has about 1.5 billion edges. So that's about 6 gigs if you store it in the sparse format. The Scalpel graph is bigger. It's about 6.6 billion edges, 1.4 billion vertices. That's 38 GB if you store it in the sparse form. And the largest publicly available graph is this web graph, which is about 128 billion edges. And that is, if you store it in the sparse form, 540 GB. So they're big, for sure. This is on the order of billions of vertices. And if you stored it in the adjacency matrix form, it would be too big to fit in any machine, because that would be 3.5 billion squared, which is intractable. So we have to store them in the sparse form. And they're sparse. So you can see the relationship between the number of edges and the number of vertices. Here, maybe 3 times, or 30 times, I guess. So the average degree is quite low relative to the number of vertices in the graph. The average degree, the maximum degree is equal to the number of vertices in the graph, but the average degree, you can see, is on the order of 10 to 100. So it's even less, 1.4 billion vertices, 6.6 billion edges. So the average degree is less than 6. And this one, the average degree is less than 100, because the difference between 3.5 billion and 128 billion is less than 100 times. Yeah. So they have this structure, and they can also be highly skewed. So in most social networks, there's this skew of degree, where if you plot all the vertices by their degree, and this is basically like a histogram, you see that most of the vertices have very low degree, and a few of the vertices have very high degree. These are heavy nodes in the graph, famous people in a social network. And there are a lot of studies about this, and this is called the parallel distribution. And usually in parallel distributions, vertices follow this, something similar to this function, where the number of vertices with some degree is inversely proportional. The number of vertices with higher degree decreases. And it makes sense, because there's more regular people than famous people. And usually p, so this is some alpha, which is a constant degree raised to the negative p, where p is something between 2 and 3. So this is some setting. If you want to generate these things, you could set this in your generator, or you can empirically find it from your graph. So some problems that we're interested in running on graphs. So social networks are one of these classical applications for graph representations. So for example, on a social network, you can find people in similar circles. For example, Facebook will recommend you friends from previous points, previous circles in your life. Who did you go to high school with, or who did you go to college with? And how do they find those? Well, they probably ran some sort of graph traversal through their social network and found people who are maybe 2 hops away from you and people who are in communities similar to yours. You can find all the common friends of someone, so this is something that they also report, like if you add someone, they'll tell you how many mutual friends you have. Or, yeah, they recommend you new people who you might know but you haven't added. And recently, I guess, not so recently, but they're also interested in recommending products. So they also, like on your feed, you will see not only people, but they serve you ads. And so they want to find relevant ads to you, ideally. Maybe a bit lower level, but still something that people are interested in running on social networks is finding clusters or groups of vertices that are well connected in the graph. So clusters are, in your graph, you have clumps of vertices that are well connected to each other, but they're not super well connected outside of the cluster. So like inside the cluster, it could represent, I don't know, a community, some like a school or an interest group or something. And you could also use it in different types of graphs, like outside of social networks. You could, in the web graph, you could use it to try to detect fraudulent websites, or if the graph was people use it for like money laundering, or trying to detect money laundering in like transaction graphs. It can also be used for document clustering if the nodes represent documents and the edges are connections between maybe like similarity in terms of meaning or topic. And clustering is also a classic unsupervised learning problem. So trying to identify clusters in the graph without external information. Any questions you have? So the main algorithm that we will be focusing on today is just trying to optimize breadth for search. Just a classic graph algorithm. So breadth for search is like this. You have a graph, and you have some source vertex S, and you want to visit the vertices in order of their distance from the source vertex S. So, for example, if this is your graph, and the source vertex is D, we build out what is called the BFS tree, which is the root is the source vertex. Everything at level 1 of the tree is distance 1 away from the root. Everything at level 2 is distance 2 away from the root, and so on. So the length of this thing is the maximum path length between the source and any other vertex in the graph. And this is a tree. So if we started at D, the first level, D is connected to B, C, and E immediately. And then 2 hops away from D is A. So B, C, and E are at level 1 in the tree, and A is at level 2 in the tree. And there are several possible outputs for BFS. You can output a vector of distances, which is one common formulation. So distance 0 is the root, distance 1 is everything 1 hop away, and distance 2 is everything 2 hops away. Or you could output the BFS tree. So rather than outputting the distance, you could output a vector of the same length, but rather than the distance, you put in the parent. So you put the parent in the BFS tree. So everything with distance 1 has D as the parent. And everything with distance 2 would have whatever connected it into the BFS tree. So here, B would be the parent of A in that vector. And that is the same length vector, like this is equal to the number of vertices, but you can just output either or both. And you can get if you have the parents array, you can easily get the distance array, because you would find things that are 1 hop away by finding everything with the parent of D, and then you would find everything 2 hops away by everything with the parent of everything that you just found with 1 hop. And you can find the distance, or you can go backwards, like that's how to reconstruct the entire BFS tree. But you can, if you start from some vertex, you can find the distance, but you just follow the parents until you get to D. So you kind of like, you start from the leaf in the BFS tree, or you start from any node in the BFS tree, and you go up until you reach the parent. And you can do that because you have the parents array. So every entry corresponding to a vertex is the parent, and you just follow them in the tree. And BFS, it is a simple algorithm. It's like one of the more lightweight ones, but it can underlie a lot of other more intensive algorithms like Between decentrality, eccentricity, max flow, and others, cycle detection, and so on. So we'll first go through the serial version of this, and then we will look into how to parallelize it. Are people already familiar with how to run BFS in serial? Has anybody not seen the serial BFS algorithm? So we'll just go through it, but maybe not in great detail. So the serial BFS algorithm, a very common one is like this. We're going to output the parents array, a BFS tree. And so we have to initialize the parents array, which is equal to the length equal to the number of vertices we have, which is n. And we also need to initialize a queue, because the classic serial BFS is you have a queue, and you have some stuff in the queue, and that represents the next vertex that we're going to visit. So we initialize the queue. The maximum size of the queue is also the number of vertices, because the things that are going into the queue are the vertices in the graph. And this is just initializing the parents array, so everybody gets -1 in the beginning. And in the end, everything that will have -1 is the things that are not reachable from the source. So in the beginning, we initialize the queue with the source. So queue of 0 is the front, and we put the source vertex. That's something we would get from so the parameters are like number of vertices, number of edges, the graph, the source vertex. And we would put the source in the front of the queue, and we just set parent of source, a source, to note that it's been visited. So we're filling out the parents array in this whole flow. And we just say we have the front of the queue is 0 and the back is 1. So we have 1 item right now. Setup. And this is the main loop. So while the queue is not empty, so while queue front is not equal to queue back. Oh, and we're going to assume that the graph is in CSR. So the main, I would say that the main step in this function is you look at the front of the queue. If it has not yet been visited, you look at all the neighbors of what is in the front of the queue, and if those have not been visited, you add them into the queue. So the only time that you have to access the graph is to look at the neighbors. And we do that in CSR by, you have your vertex, you look it up in the offsets array, and you follow that into the edges array. So the current is just implementing what I just said. The current vertex is the front of the queue. The degree is of that vertex is offsets. So this is the offsets array in CSR. The degree is like the next item in offsets minus the current item in offsets, where the index is given by your vertex. And you iterate through the degree. So this is why we need to get the degree, because it determines the length of this for loop. And this for loop is just going through the neighbors. So the neighbors now accesses the edges array, and you get the item, or you get the neighbor by doing offsets of current, which is the start of your neighbors in the edges, plus I. So I is ranging from 0 up to degree. And if that neighbor has not yet been visited, so parent in the parent array, parent of neighbor is equal to -1, then you set parent of neighbor equal to current, because we reached it through the current vertex, and then we put it into the queue. And that's it. It just goes back around until the queue is empty. So probably the only part of this that may be unfamiliar is this access into CSR, because the high-level flow is always the same, like you have a queue, you add stuff into the queue until it's empty. And the only thing that changes with the graph representation is how you access the neighbors, because the parents array and the queue are like something maintained outside of the graph. It has nothing to do with how you store the graph. Like if you stored it in COO or CSR, the parents array would be the same. It would depend on that. Any questions about this part? So what is the most expensive part of this? Yes, checking the visiting neighbors, and I guess from that, checking the, just getting the neighbors as well. Because accessing the neighbors takes m random accesses, where m is the number of edges in the graph. And the parents array, you're going to visit it. Well, you're going to check the parents possibly m times, but we update the parent and the queue only n times. Usually n is less than m, right? Like constant factor. Oh, yes. Why does it need to use random access? So the access to the neighbors is contiguous. Like once you get to the start of the current vertex's neighbors, you just read them left to right. But where that vertex is anywhere in the CSR. Good question. And also, the access into the parent array is random because you're checking the parent array for every neighbor. There's m possible neighbor checks, and the neighbors could be anywhere as well. It's just like the IDs of the neighbors are contiguous, but the actual neighbors themselves can be anywhere. So this is just the same code, but I put it a bit smaller. This was the initialization, this was the actual loop. And so if we want to think about which part is more expensive, we can think about how many cache misses it takes. And the reason that we're trying to reason about the cache misses is there's not a lot of actual compute going on in this thing. Like the only part that we're only setting these arrays more or less and accessing the neighbors. There's no, like we're not actually doing that much output. And yeah, the only thing that's getting updated really is like the arrays and maybe this variable like the size of the queue. So how can we analyze the cache miss? Well, let's just assume that it's cold, which means that there's nothing in it at the beginning. And if the cache size is less than the number of nodes, and we have 64 bytes per cache line, and they 4-byte ints. So that means there can be 64 divided by 4, which is 16 ints per cache line. So there are n possible vertices. There are 16 ints per cache line, so that's n over 16 misses to do the initialization. Because you just have to, this is the initialization, the size of parents is n. There's n over 16 cache lines in parents, and you just read them left to right to do the initialization. And similar for the dequeuing, we're going to add or pop off at most n vertices through this entire thing, and we do that contiguously in the queue, because the queue is just an array, and we're moving it. We're adding stuff to the end, and we're dequeuing stuff as we go along. So we're going to touch at most n memory slots for that, and they are next to each other. So that again is going to be n over 16 over the life of the algorithm. And then we actually have to access the offsets array, and that takes n. And notice that we didn't divide by 16 this time, because, so this is when we offset it, or when we access offsets, offsets is current plus 1 minus current. But current could be anything, because we're just dequeuing. This is a vertex that we're dequeuing from the front. We're not guaranteed that the vertices are next to each other in the CSR. So that's why it's n. And to access the offsets array, similar thing. It's bounded above by 2n plus m over 16. So 2n is above from accessing the front of the neighbor list. And divided by m over 16 is because once you access the edges, they're left to right in the CSR. So you can take advantage of the cache line for reading those. And accessing the parents array is m. So yeah, like you were saying, this is the most expensive part because there's no locality in accessing the parents array. They could be anywhere. Oh, yeah, and the same for MQA and BQA is also n over 16. And if you add them all up, you get this thing. More questions on how we got these numbers for any of them? So, like I said, the only new part, probably from algorithms that you've seen, is this access into the CSR to get the edges. And that gives us m over 16 for accessing the edges array. And so this part is the only part that changes if you change the graph representation. So if this was adjacency matrix, it would take n squared over 16 to read the edges array, because every time you have a current vertex, you have to read the whole neighbor. You have to read n slots to check where the neighbors are. So if m is much less than n squared, you can see that this is a huge savings in terms of access. So how can we reduce the misses in the parents array?
Edges have to be sorted to access the parent array sequentially. So.
Yes, and we can, the CSR can store the neighbor list sorted, like each individual neighbor list.
Oh yeah.
But they may be far still.
Okay.
Like, you could, like, the neighbors could be like 1, 100, 1,000, and they would be sorted, but they're like they're not next to each other in the parents. So, yes. But yes, it's a good thought. Yes, we can assume, or we can store the CSR sorted individually, and maybe in this case, since we're trying to optimize the access to the parents array, we can change the representation of the parents array. So yeah, so when you're optimizing these graph algorithms, there's several, I guess, like degrees that you can try to optimize. One is the actual graph representation, like CSR. And then another is I would say, like these metadata kind of arrays, like the queue, or the parents array, or here there's only the queue and the parents array, but in other more complicated algorithms, there may be other metadata arrays. So right now, we directly use the parents array to store both the parents and the, to store both the parents and the, like whether or not they have been visited. And one idea is maybe we could try to decouple those. And I think this is a classic optimization BFS. You have, right now, this checks if it has been visited. And if it has not been visited, then we update it. You can keep a separate array for visited and a separate array for parent, because visited only requires 1 bit. So to try to reduce, so right now, we have to access the parent array m times, because we access it once per edge. But we can try to cut that down, because actually, we only need to update it n times, because the BFS tree is at most n vertices. And so to try to cut that down, we can introduce this hasn't changed the code, but we're going to get there. The high-level idea is that we are going to try to decouple the visited information from the parent's information. And the visited information needs to be checked m times, but the parent's information only needs to be checked and updated n times. Does that make sense? So it's going to make this code slightly more complicated, but the idea is that we're going to try to decrease the number of cache misses. And also we can decrease the size. So like we could keep a separate array of ints that's visited, but better would be to keep an array of bits because you only need to check whether it's visited or not, so you only need one bit. And I can cut down the size divided by 32, assuming these are 4-byte ints. And if that bit vector can fit in the cache, then you can reduce the number of cache misses because you are still doing random access into this bit vector, but if the bit vector is smaller, then hopefully it can fit in the cache better. Not a theoretical thing, like you have the cache size, you have the bit vector size, because you know how many edges, or you know how many vertices you have. However, it trades off a little bit of computation, because you reduce the space, but I have to do some bit manipulation to determine the index. So this is also another common trade-off, which is you can save the space, you trade space or you save cache misses, but you pay some computation to do it. And sometimes that can help you because, as we know, computation is much cheaper than cache misses or data movement. And so sometimes you may even find it worth it to pay additional computation time to save data access time. Yeah, so DFS is like, it's not a very complicated algorithm, like the whole thing fits in these few lines, but I think it is an interesting example of some nice tricks that you can use. Okay, so how are we going to do that? Well, we are going to make a bit vector. This is how big it needs to be, which is 1 plus n over 32. So n is the number of vertices. 32 is how many bits we need. And visited is now the size. And you still keep a parents array, still there. But we just paid a little bit of extra space to keep this thing. And in the beginning, none of them have been visited. Once we enqueue the source in the initialization, now you have to find the location of the source. And so this is how you do the bit manipulation. Visited is an array of ints. There are 32 bits per int. And so this is the index of the whole thing, source over 32, which is which int are we in. And then source mod 32 is which bit are we in that index. So we're going to reuse this indexing here. So now, so every time we update parents, we are first going to check if that vertex has already been visited. I'm going to check that by maintaining this visited array. If it has not been visited, which is this thing, visited neighbor of 32 exists, and you shift 1. Oh, okay, yeah. So this is bit manipulation. So this whole thing is visited neighbors of 32 is accessing the int that neighbor is located, is the bit. Sorry. This visited of neighbors of 32 is the int in the whole visited array that corresponds to the neighbor that we're interested in. And so we're taking that one int, and we are making a mask, which is one left shifted by which index we're interested in that int. And then you add them together, and it will say 1 if it has been visited, and 0 if it has not been visited. So this is just saying, has the bit corresponding to whether my neighbor has been visited, has it been set or not? And if no, then we are going to say that then we're going to set it, which is through this. And then we are going to do what we did before, which is set the parents array as current. So this is building out the DFS tree and updating the queue. That part doesn't change. So there's some trade-off, like this bit vector thing is only worth it if your number of edges is big enough, but it can cut down on the cache misses if the bit vector can fit in the cache, and then you do random access to the bit vector rather than so many random accesses to the parents. everybody go, okay, I like how this bit manipulation works. This is how you extract out whether or not one bit is set in an arbitrary location in the array. And notice so far that these are all serial implementations, like we have not even introduced parallelism yet. And yet, there are still interesting things that you could do. I mean, serial is usually cache optimizations, but these are cache optimizations, and you can teach an entire class on cache optimization, so it's still worth talking about. So now we're going to look into parallelizing this thing. Okay. And the way it works is rather than keeping a queue, still kind of a queue, but now it's called, in parallel they call it a frontier. And the frontier means the set of active vertices at some phase in the algorithm. And the way that the frontier is built is it's just the outgoing neighbors of what was on the previous frontier. And the beginning is just the source vertex. And the reason that you can build these parallel, and everything that is on the frontier can be processed in parallel, because the ith frontier, everything that is on the ith frontier is distance I from the source. So in the beginning, the 0th frontier just contains the source, so it's distance 0. Then in the next phase, everything, all the outgoing neighbors of the source are on the frontier, and they're distance 1 away from the source. And then in the next round, we put all the neighbors of what was distance 1 away, so all those neighbors are distance 2 away. And we continue until the frontier is empty. And yeah, so each frontier can be processed in parallel. And you can parallelize over the vertices and the outgoing edges. So the way we build the frontier is very similar to the way that we built the queue. Like the main step in building the queue was you look at the front, you look at all the neighbors of the front, and you put the neighbors at the end if they have not been visited yet. And similarly, the way that we build the frontier is basically the same, but in parallel. We look at some set of vertices, we add all their neighbors into the frontier if they have not yet been visited, and that is a new set of vertices for the next time. So this is the high-level direction, but adding things like this in parallel causes some issues because, well, one major issue is if you have a frontier, they may have shared neighbors. Like you have at least 2 vertices in the frontier, and they may connect to the same vertex. They may connect to the same outgoing vertex. But you don't want to add that outgoing vertex twice into the next time, because you just want to do it once. So that causes some problem. And also there's some high-level issues, which is that that we won't really resolve today, which are about load balancing. Any questions on this high-level direction? So, this is how we write the code. In the beginning, we do some initialization, and instead of having a queue, now we have a frontier, and we have an array to keep the frontier, and we have an array to keep the frontier next. And basically, the way the high-level direction is going is you have the frontier, you fill out the frontier next, and then you swap the frontier next for the old frontier. Next time you fill out the frontier next again. And as before, we still have the parents, but now we have some other side data called degrees. And we'll see how degrees is used in a minute, but degrees has length equal to n. And basically, we're going to use degrees to tell the degree of every vertex currently on the frontier, because we're going to need that for some post-processing. In the beginning, this is the same as the queue. We put the source in the frontier. We set the frontier size equal to 1, and the parent of the source is equal to source. So far, this initialization part is the same as the queue. And this part, I guess the only difference is that we parallelize it now. Like, parallel 4, 0 up to n, we initialize the parents of all of them equal to -1. That hard. It's like, I don't know, it should be small relative to the size of the algorithm, but we're proud of it. So this is the high level direction. While we have stuff in the frontier, or while it's not empty, in parallel, we explore all the outgoing neighbors of all the vertices in the frontier. And then we copy all the neighbors. So for each vertex B in the frontier in parallel, we copy the neighbors into frontier next. If they have not yet been visited. And then we set the parent of all the neighbors in the parents array if neighbor B does not yet have something in the parents array. So these things are just kind of parallel versions of what we were doing before. Like in the queue version, we were copying the neighbors into the end of the queue, and then in the queue version, we set the parent of the neighbor as the current. And then once we have filled out the frontier, once we have filled out frontier next, we set the frontier next to frontier. And then you just repeat. Any questions on this one? Oh, in the beginning it's set to 1, but we're going to update it. It is not always meant to stay as 1, but just in the start, we just have 1 because we're the source. Yes, good question. So, oops, in here, we're going to, once we copy all the neighbors into frontier next, we have to update frontier size equal to this, how many we copied in. So, like this looks very simple, but there are a couple of small issues that come up. One is, how do you know which index in frontier next you're going to copy the neighbors of vertex B into? So when we had a queue, it was easy because we had queue start and queue end, and just copy starting from queue end. But now you have a set of neighbors, or sorry, you have a set of vertices, and you have an array, and you need to copy all of their neighbors into the array, ideally contiguously. Because like when you process the frontier, you have frontier size, and the parallel for loop is over frontier size, so they need to be in the front. So that's one problem, because you're doing all of this in parallel, so you cannot do it left to right. Like if you were doing it serially left to right, like we were doing it before, we know Q next because Q next just increments with the degree. But now if you're, even in the case, let's consider we have 2 vertices on the frontier, the second one doesn't know the size of the first one. And so like you would like to copy the second one starting from the end of the first one, but you don't know it up front. And so, or you don't know it without additional processing. And so we need to do a little bit extra to figure that out. The second one is, what if multiple vertices in the frontier have the same neighbor? Any of them are valid, but only one of them should set the parent in the parent's array, and the rest of them should not set the parent, because it should know that it has already been visited. Are the issues clear? So how would you solve these problems? We can start with the first one. You have a set of vertices. You know their degree. You have the CSR. But in parallel, you need to copy them in to an output array contiguously. You can do both. You can do pre-processing. Can you broadcast? Can you say more about that? Oh, I see. Yes, it can be even easier because we're in shared memory right now. So everybody, all the threads or all the processors can access the whole CSR, and they can access the whole parents array, then they can access the whole, degrees array. Oh yeah, I guess important is that we remember that there's also this degrees array. Yeah, they can all access the whole frontier, they can all access the whole frontier next, and they can all access the whole CSR and the whole degree and parents.
Does the degrees array tell us how big each chunk of frontier is?
Yes, good. So we can fill out the degrees array to tell us the degree of every vertex. So we have all the vertices in the frontier, and we can just look in the CSR to tell us what is the degree of every vertex. And then how do we translate that into where each one should write in the frontier next?
Would you just like prefix sum all the degrees and then those are your offsets for each?
Yeah. So very good. So the first step is that we need to find the degrees of every vertex in the frontier, because that's going to tell us the maximum size of what we could be copying into the frontier. And the second step is, but the degrees are like, they're not increasing, and we need to find increasing memory slots to put them in. And so to get that, we do prefix them to find the starts. So this is, in some sense, it's sort of similar to building a new CSR, where the new CSR is just the vertices that are on the frontier. Yeah, exactly. So how are we going to do that? Well, we get the degrees, like you just said, by copying in from offsets. So this is how we would get the degree from the CSR offsets. The frontier of I is the vertex, and the degree is just the vertex ID plus 1 minus the vertex ID. Sorry, offsets of the vertex ID plus 1 minus offsets of the vertex ID. And then now, after that, for degrees of 0 up to degrees of frontier size, we filled in the degrees array. And now we perform prefix sum on the degrees array to tell us the starting points. And this, so if you do an exclusive scan, which starts at 0, and then just takes in everything up to that point, but not including, it tells you basically this is telling you how many, the sum of all the degrees that came before you in the frontier. And that is where you should start writing your neighbors. So that solves the first problem. Great. So, because we want to be careful, like, not to sequentialize any step by accident, because that will sequentialize the whole thing. So we can do this in parallel, and the maximum size of frontier is n, because the frontier cannot be bigger than the number of vertices we have. And the maximum number of edges copied in is n, because you cannot copy in more edges into the frontier than number of edges that you have. So now we have this. Well, we have something in the frontier size greater than 0, parallel for over everything in the frontier, so 0 up to frontier size. And some vertex is, so this is the current vertex under consideration of this thread, which is frontier of I. You can just think of it as every processor gets one I, and they're all working in parallel. But they're not necessarily all working in lockstep, like they can work however quickly they need to. And yeah, so index is degrees of I, and the degree is just offsets of vertex ID plus 1 minus offsets of vertex ID. And now we go over the degree. the neighbor is, yeah, this is just reading the edges array in the CSR to get the neighbors. And this part is a little bit subtle. So we are only copying the neighbors once. We should not repeat the same thing in the frontier. And so this is how you would do that. If the parent of neighbor is -1, we can replace this with the vector that we had earlier too. But just for simplicity, if the parent of neighbor is -1, which means that it has not yet been visited. And so I'll tell you in a second what this compare and swap is. But you can compare and swap with the location, previous, and what you want to put in. And basically compare and swap is an atomic operation that checks. Atomic means that you're guaranteed to execute the whole thing in a block. And it takes in this location, and it checks if the location value is equal to old. And if it is, then it puts in new, which is v. And if it is not, then it will do nothing. And so this is how you guarantee that only one vertex is going to write in parents of neighbor, because only one of them is going to, so it may be that several threads try to write this thing, but only one of them will win in the sense that it will go first, and then it will put in its vertex in the slot for -1, and all the ones that come after that will see v here, so they will do nothing, because it will not be -1.
How does this work? Both, let's say, two processors have access to whatever you're writing to, one is a part of that, with multiple, then the compare swap both,
Yeah, it's a good question. Isn't there an issue with compare and swap? Because like both of them can read -1, but then one of them will write v, its own v first, and then you don't want the other one to write its v. Compare and swap is it's an atomic, so it means it's guaranteed that the whole, it's only like a few lines of code. It's like if the location is equal to old, write new, otherwise nothing. And if you call this atomic, it's not the same as just replacing it with a tiny block of code. You're guaranteed that the thread will execute that whole block with no other interrupts inside. So one thread will execute its whole compare and swap, then another thread will execute its own compare and swap. So that is, yeah, that's the semantics of atomic operations. Good question. Yeah, so that's why you can't just say, that's why we can't just say if parent of neighbor equals to -1, set v. This compare and swap is something more subtle for parallelism.
How would you do this with a bit vector where everything is packed into like one word? Or like, you know, just like you would need to like how would there, is there like a compare and in place or something like that, or
No, that's a good question. So how would you would also want to atomically update the bit vector if you're using the bit vector. The compare and swap, it only works for like fixed size. So there's a compare and swap for like 32 bits. There's some work, and actually it's only like 32 or 64, so like smaller or bigger. It's not really supported, but you can read in the whole chunk, that 32-bit chunk that you're interested in.
Yeah.
You can compare and swap it with the updated version by oring in the new thing. So you generate, you have old, which is just what was in the bit vector, and you have what you want to be new, which is that chunk with one more bit set that you would get by
you
creating
just
the mask.
locally do that and then
Yeah, you locally do that and you put it in the compare and swap. So that's a really good point. Compare and swap is a bit limited in that it only works on fixed sizes. Like it doesn't work all the way down to 1 bit, and it doesn't work for like arbitrarily sized arrays. You cannot compare and swap in like 1 gig. You can compare and swap in like 32 bytes or 64 bytes. So once we have that, one of them, oh yeah, and compare and swap returns 1 if it was successful, and 0 if it lost the race. By lost the race, I mean did not succeed in putting v in the slot. And so only one of the neighbors is going to win this. And then that is going to update the frontier next with its ID. So we only want to put every vertex at most once on the frontier. Like, it's not wrong, I guess, to put it multiple times there, but then it's wasted because we'll just explore the same outgoing edges several times. So you want to minimize, or you want to make, you don't want to do more work than the serial version. And the serial version only explores every vertices outgoing neighbors at most once. And so this is going to guarantee that same thing, that every vertex is going to appear on any frontier at most once. And where are we going to write it in the frontier? We are going to write it in index, which is the start, what we got from the prefix sums of the degree, plus j, which is the local, j is like the inner loop over the degree. And otherwise, if we failed, we are going to write -1 in the outgoing frontier. And the reason that we have to write something, either neighbor or -1, is it's a bit complicated because you have a bunch of outgoing neighbors, and maybe some of them will not show up on the frontier because somebody else has already written them on the frontier. But you don't know how many of them would be up front. So we're going to write for all the outgoing neighbors something in the frontier, either the outgoing neighbor or -1 if it has already been written somewhere else by somebody else. And so after that, now we have a bunch of valid neighbors and we have a bunch of -1s. But we wanted them all in the front because in the next frontier, we're going to do the same loop, and the loop needs to go over 0 up to frontier size. But now we have maybe more than frontier size elements written. We have frontier size neighbors, but we have more than frontier size neighbors plus -1s. And so now we need to somehow put them in the front. And I claim that it can be, you want to filter out everything with -1. And I claim that you can do it with prefix sum. Questions? How to do that with prefix sum? Yeah, so this is, I don't know, like, BFX is, it's not so complicated, but it's really nice because it can illustrate several of these nice tricks, like just using prefix sum. So it illustrates a lot of examples of how you can use prefix sum in parallel to not sequentialize the algorithm. Everybody writes something, and then in the end you figure it out. Or like, everybody needs to write in their own start location, but you need to figure out where everybody starts. Okay, so this is just going through the iterator of the neighbors in the frontier. We copy in, we computed the starting points, so degrees has already done the prefix sum. If your neighbor has not yet been explored, yeah, so I guess I have already gone through this, but since other neighbors may have the same outgoing neighbor, only one of them should add it in. Otherwise, just a -1, and in the end, you filter them out with prefix sum. So how would you pack them to the front? So now you have an array. Some of them are greater than 0, and some of them are -1. And you want to put anything greater than -1 into the front of the array. You can use external space as well. A little bit.
The binary operator something like, as long as it's a -1, you ignore the subset until you get to one that is not -1. Then you build the not -1 until you reach -1 and you shift everything over.
So what is the input to the prefix sum? You can, so you start with the array, like neighbors and -1s. You can build some other array as the input if you want.
You use the size of the -1.
What do you mean by the size of the -1s? exactly what you said. Right now, it's the situation, we have frontier next with some negative ones and some valid stuff that we want to keep around. And we can build a separate array, which is 0 if it's negative 1 in that slot, and 1 if it's not negative 1 in that slot. And we run the prefix sum over this array. And in the positions where there is something, it is going to be where, if you only look at the places where there was something to write, the indices will correspond to where you should write them in the output to put them in the front. Because what is this? This is basically how many elements do you want to keep that have come before you. And then after we have built this thing, then we can fill in the frontier, which is if flags of, in parallel, if flags of I was equal to 1, then we're going to copy in the value as frontier, which is frontier, the index is the result of the prefix sum of I equal to frontier next of I. So we had frontier next, which was this, like some negative ones and some stuff that we actually are interested in keeping. And now in the next round, frontier is going to contain only the stuff that we're interested in keeping starting from the front. And we can get frontier size for the next step by just the last element in this prefix sum is how many elements were there. And I promised you that we would go through compare and swap. So compare and swap is this atomic operation. It takes in 3 arguments, a pointer to some int, an old, and a new. And it is guaranteed, once it starts, it is guaranteed to execute this whole section without interruption, without anybody else intervening. And it's very simple. It's like while what is, or it is if what is in the pointer is not equal to old, return false. And if it is equal to old, then you put in new and you return true. So this returns true if it succeeded in updating the value of the pointer to new, otherwise it does not update anything and returns false. And so we used that previously to write only one neighbor, or only one instance of an outgoing neighbor into the frontier next. And you can also use it to implement locks, because the simplest lock, so a lock is something that gives exclusive access to an area, or like a data item or something. And in the simplest form, it can just be thought of as 0 or 1, where 0 means that it's free and you can access it, or 1 means that somebody else is accessing it. And so you can compare and swap in. If you're trying to access that area, you first try to compare and swap in the pointer, 0 and 1. So if it's not 0 at that time, you cannot access it, and you just have a while loop to come back around. So that's the end of BFS, more or less. The span. So the number of iterations, the number of frontier iterations is equal to the diameter of the graph, which is the longest path. Each iteration has several steps that we just went through. Basically, it has filling out frontier next and making sure that it's not repeated or anything like that. And that's bounded above by log m, where m is the number of edges, because at most we explored m outgoing edges, but we did that all in parallel. So that's where the log comes from in binary forking. And so we have to be careful. Like if any part of it was sequentialized, like going over the vertices in the frontier, there would be an extra n plus log m here, which is unacceptable because, as we saw in practice, m is something like 10n. The span in the end is d, the diameter, times log m. And the work, so we want to do no more work than the serial algorithm. The serial algorithm does n plus n work because you explore every outgoing edge at most once, and you touch the parents array at most n times because you have to update the parents array. So that's where serial is easier to reason about why it's n plus n. But for parallel, we want to maintain this bound. So the sum of all the frontier sizes over the entire execution should be equal to n, because we're not repeating any of the outgoing vertices with all the prefix sum stuff that we were doing before. Every outgoing edge gets traversed at most once, which is m total visits into the parents or the visited bit vector. And the work of the prefix sum on each iteration is at most, so we're doing prefix sum only on the things in the frontier, either the degrees or the actual items in the frontier to determine how to pack them in the front. So the work of that is bounded above by n, because prefix sum has linear work in the size. And then the work of the filter, which is just through prefix sums, is at most m, because it's equal to the number of edges traversed. So total is m plus n. And the reason that we needed to pay a little bit extra in terms of the prefix sum is to make sure that this doesn't grow, this stuff doesn't grow arbitrarily large. Because if you copied the same vertex onto the frontier many times, you would explore the outgoing edges many times as well. This is just some data. So we generated a random graph with n equals 10 to the 7 and n equals 10 to the 8. And so this is 10 edges per vertex, because you just divide it. And then if there's 40 cores, there were 40 cores in this experiment, and they drew the strong scaling. So x is the number of threads used, y is the speed up relative to single core time. And speed up. So there's two-way hyperthreading, which means that there's 2 threads per core. So that's why it goes up to 80. And it goes up, I don't know, not bad, so up to 40-ish. Relative to the one thread execution of parallel BFS. But, which is different from the execution of serial BFS. Serial BFS is what we were doing first, but it has, like with the queue, but it has less work overhead because it doesn't need to do the filtering and the prefix sums to find out the next frontiers. So that's why the relative speed up is less, up to somewhere between 20 and 25, rather than somewhere between 30 and 40. So this is another thing, which is when you run these scaling plots, it is more fair to consider the best serial algorithm. And in the beginning, when we were talking about efficiency speed up, I said you should compute speed up relative to the best serial algorithm because it may be better than the single threaded execution or one processor execution of your parallel algorithm. Because if you just run this on one thread, you still have to do the filter and the checking and stuff like that. Now, on one thread, the serial BFS is 54% faster than running the parallel version on one thread. So sometimes you may read in papers that they ran it versus the one threaded time, and like the scaling plots are beautiful. But if you run it against the best serial algorithm, you may find that the scaling plots are less beautiful. So we'll do this. One thing that we didn't quite address is non-determinism. So with this compare and swap, there can be many incoming vertices trying to update or trying to put in one outbound vertex. And if you run this code many times, in shared memory, the scheduler schedules the threads, which is some underlying thing from the OS. And it's not guaranteed that in different runs, that like the same thread will win every time. It's not, well, first it's not guaranteed that the same thread is assigned to the same iteration. And second, it's not guaranteed that the same thread will win every time. And so if you run this multiple times, you may get different winners for who wrote in the parent of neighbor. And it's not deterministic, which is not ideal because it's harder to debug. Like, you want to verify the parents array, and one easy way to verify the parents array is you run the serial version, which gives you something, and you check it against the parallel version. But this is very hard because the serial version is deterministic, and it will give you one answer. And if you try to do this validation, it may be correct, like this version may be correct, but it doesn't check against the serial version. And so ideally we would like to, for debugging purposes, put in some deterministic version. And the way we can do that is we use a different atomic called the rightmin, which is the semantics above. And rightmin is kind of as it sounds. You have an address, and you have a new value that you want to write. And you have an old value, which is what is currently at the address. And while the new value is less than the old value, if you successfully compare and swap the new value in, then you can exit. Otherwise, the old value is equal to what is currently at address, and you come back around. So you build this with compare and swap. But what is this going to do? It is only going to succeed in writing if what was at old value is less than new value. So in the end, there are many threads trying to write to the neighbors, or trying to write to the parent array, but the smallest parent is going to win in the end. So that's how you make it deterministic, because there are many possible parents, which are all the possible incoming edges for a given vertex, but only the one with the smallest ID is going to end up there in the end. So the smallest value got written, so we substitute in with rightmin, and this is where's the same as before. If the neighbor won, or like, so this is going through, so you're in some parent, and this is going through the degrees of that parent, or the, yeah, okay, this is going through the neighbor list of that parent. So neighbor is edges of an offset of v plus j, and if it won, then you avoid revisiting it by setting it to something negative. You set the neighbor equal to the frontier, or sorry, you set the neighbor onto the frontier next, and this part is the same. Some of them are neighbors, some of them are -1, and you filter out the negative ones to pack the true neighbors into the front. On 32 cores, an optimized deterministic BFS using rightmin is about 5 to 20% slower than the non-deterministic version. And the reason is because before there was just one compare and swap per thread, but now there may be multiple if you keep trying. So you pay a little bit for determinism, but at the price, but the price of the non-deterministic version is that it's hard to debug. So it's trade-off between more certainty and more performance. Out of 10. So we'll just end there. Thank you. So next time, again, there's no lecture, but if you have any questions, we can go over any part that we had in the previous lectures. Thank you.